In the last chapter, we left an unimplemented function, and there are a few more things left for us to do to actually call our program a static block generator. We still need to process multiple files in the directory and create an index landing page with links to other pages. Our HTML DSL currently does not support links or other content modifiers such as bold and italics. We should add this so we can use them when creating an index. Up until now, we've passed strings to structure, creating functions such as paragraph and headers. Instead, we can create and pass them a new type, content, which can be regular text, links, images, and so on. So let's implement what we've just discussed. We can follow the compiler errors and refactor what needs to be refactored. In the HTML internal module, we add another string new type called content. So now the header should take the content. Before the function expected a string, and now we have a content, so we need to get the string out of the content. We can do the same thing we did with the structure before. We create a helper function which extracts the strings using pattern matching, and then we compose it with what we had before, which should work fine. And we should do the same for the paragraph. Instead of string, we pass a content, which we can get rid of using the getContent string we just implemented. A quick note here, I forgot to mention previously, we use the $sign to avoid parentheses. This $sign is a function application operator. Using it is similar to using the default application operator, but the dollar has very low precedence. So the following are the same. When we put the dollar in front of the map function and the rest of map application, it's the same as wrapping this whole expression in parentheses and then wrapping it in unordered list. Because regular function application has high precedence, the following usage results in a compilation error. Because if we don't put a dollar or don't put the parentheses, the Haskell will do it for us. And it will do it wrongly and then will fail and we'll get a compilation error. So we have to be explicit and put the parentheses or dollars where they belong. Now we have to create helper functions for creating this content. For the text, for the link, for image, and so on. First one, the text. We escape the string and wrap it in the content. For the link, we have to take a file path, the content, and return a new content. We cannot use the element function we had before because it doesn't take attribute, and links should have attributes for the href. So let's create a new function for creating elements with attributes. It looks similar to the element function, but instead of just creating tags and wrapping the content into it, we add the attribute inside the tag. Now we can create a link and pass it an href. And note that we have to escape it. Image also needs an attribute, but image is not the usual text. It doesn't have an opening and a closing one, so we cannot use the element or element attribute functions like we did with other elements. We can create a new function, or we can just hard-code it here for now and see in the future if we're gonna need to extract this into a separate function. And the other two are quite simple. We take the content, create a new element, and wrap it in the content. After doing all this, we have to remember to re-export all the new functions for our users. Now when we build, we're going to see a lot of errors in the convert module because we changed the API, we broke it. Now we have to go and fix it, but luckily the compiler tells us where the stuff is wrong. In the first case, we were passing a string right to the header, but we can't anymore. We have to create this HTML text first. Same for the paragraph. We cannot simply create a paragraph. We have to wrap a string in a text and then pass it as a paragraph. In case of list, we have to do this for every element. So while we're mapping and wrapping stuff in paragraph, we're wrapping them in text first and then in paragraph. At this point, everything should compile and work as expected. With our extended HTML DSL, we can now create an index page with links to other pages. To create an index page, we need a list of files with their target destinations, as well as their markup, so we can extract information to include in our index page, such as the first heading and paragraph. Our output should be an HTML page. In other words, we need to implement the following build index function. Build index takes files, and what do? We want to return a valid HTML, which needs a title and a structure. The title could be simple block. And for the structure, we can start with a header, which is a link to the index HTML page, which just says blog. And then we can list all the posts. Let's create a separate function for this. We have to do something with the files. Because it's gonna be the same for every file, we know that we should probably map and apply some function and or transformation to every file. And then we have to concatenate them together into one HTML. We can map and concat, or we can fold map as we've seen before. Our f is some sort of make review function, which takes a tuple of a file and a document. So what should we do? It depends on the document. If the document has a header and some articles, we can use that header to create a new subheader and link it to the file. We can also get some preview from the article, convert them to the structure, and omit the rest. We just say whatever, ... And if we don't have a header and an article, it means we probably have one element or something's missing. We can just link the file using the file path. At the end of the day, we want an index with simple previews to all the blog posts that we have. We don't have any information to show, we don't show it. If we have, we try to make some kind of preview. Our general strategy for processing whole directories is going to be this. We create the output directory, grab all the file names in a directory, filter them according to the extension. We want to process the txt files and copy other files without modification. We want to parse each text file, build an index of the result, convert the files to HTML, and write everything to the target directory. While our parsing function can't really fail, trying to read or write a file to the file system can fail in several ways. It would be nice if our static block generator was robust enough that we would not fail completely if one single file gave it some trouble. This is an excellent opportunity to learn about error handling in Haskell, both in unaffectful code and for input-output or IO code. In the next few chapters, we'll survey the landscape of error handling in Haskell before figuring out the right approach for our use case. There are quite a few ways to indicate and handle errors in Haskell. We're going to look at one solution, using the type either. Either is defined like this. Simply put, a value of type either AB can contain either a value of type A or a value of type B. We can tell them apart from the constructor used. For example, left true has boolean on the left and right char has char on the right. With this type, we can use left constructor to indicate failure with some error value attached, and the right constructor with one type to represent success with expected result. Since either is polymorphic, we can use any two types to represent failure and success. It's often useful to describe the failure mode using NADT. For example, let's say that we want to parse a character as a decimal digit to an integer. This operation could fail if the character is not a digit. We can represent this error as a data type parse digit error. Our parsing function can have the type character to either parse digit error or an integer. When we implement our parsing function, we can return left on an error describing the problem and right with the parse value on a successful parsing. Either A is also an instance of a functor and applicative, so we have some combinators to work with if we want to combine this kind of computations. For example, if we had 3 characters and we wanted to try and parse each of them and then find the maximum between them, we could use the applicative interface. The functor and applicative interfaces for either A allow us to apply functions to the payload values and delay the error handling to later phase. Semantically, the first either, in order that returns the left, will be the return value. We can see how it works in the implementation of the applicative instance. In the implementation of apply, we return a left as soon as we see it and keep going if it's a right. At some point, someone will actually want to inspect the result and see if we get an error with the left constructor or the expected value with the right constructor, and they can do that by pattern matching on the result. The applicative interface of either is very powerful and can be combined with another abstraction called traversable for data structures that can be traversed from left to right, like linked list or binary tree. With this, we can combine an unspecified amount of values, such as either or parse digit error and int, as long as they are all in the data structures that implements traversable. Okay, let's see some examples. Remember that a string is an alias for a list of characters. We can check it with the info command. So for example, if we want to apply the parse digit function to the list of characters, the result is going to be a list of either parse a digit error or an int. Because all of them were integers, we get all the rights back. A function sequence A takes a t of f of a and returns f of ta, which could be confusing, but if we substitute t with a list and f with the either error, we get a specialized version. So we go from the list of either errors to the result, which is either error or a list of our values. If we apply sequence A to the mapping we've done before, remember like we had a list of rights, we get back a right of list of integers. Well, the interesting thing is when we get an error, for example, we cannot parse an A because A is not a digit. When we sequence it, we get one left back saying we got an error. This pattern of doing map and then sequence is another function called traverse. If we traverse a list of integer characters with a parse digit function, we get back a right of the list of integers. But if one of them was not parsable, we get back a left error. We can use traverse on any two types where one implements the applicative interface, like either A or IO, and the other implements the traversable interface, like a list or some sort of map, also known as a dictionary in other languages, a mapping from key to values. For example, using IO and a map. First, import the qualified map from the containers package. Then we create 3 file mappings from output to input files, and then we construct a map data structure from a list of tuples using the fromList function. The first value of the tuple is the key, and the second one is the type. The files in this case is a mapping from file path to file path. Because file path is an alias to a string, we don't have to do any conversion. We can create a function using traverse for reading all the files. This read files takes a mapping from the output file path to input file path and returns an IO operation that, when run, will read the input files and replace their content right there in the map. Surely this will be useful later. Note, since either has a kind type to type to type, which means it takes two parameters, either cannot be instance of a functor or applicative. Instances of these type classes must have the kind type to type. Remember that when we look at a type class function signature like fmap and we want to implement it for a specific type in place of the f, we need to be able to substitute the f with the target type. If we try to do this for either, we would get something like this, and neither either A or either B are saturated, so this is not gonna type check. For the same reason, if we try to substitute f with say int, we'll get a nonsense type as well. While we can't use either, we can use either E, which has the kind type to type. Now let's try substituting f with either E in the signature. We take a lift A2 and we get lift A2 for either E. What this teaches us is that we can only use the applicative interface to combine two eithers with the same type with the left constructor. So what can we do if we have two functions that can return different errors? There are a few approaches. The most prominent ones are, first one is to make them return the same error type. Write an ADT that holds all possible error descriptions. This can work in some cases, but isn't always ideal. For example, a user that just calling a parse digit should not be forced to handle a possible case that the input might be an empty string. The second option is to use a specialized error type for each type, and when they are composed together, map the error type for each function to a more general error type. This can be done with the function first from the byfunctor type class. The applicative interface allows us to leave the function to work on multiple either values, or other applicative functor instances such as IO and parser. But more often than not, we'd like to use a value from one computation that might return an error in another computation that might return an error. For example, a compiler such as GC operates in stages, such as lexicon analysis, parsing, type checking, and so on. Each stage depends on the output of the stage before it, and each stage might fail. We can write the types for these functions. Tokenize takes a string and either returns an error or a list of tokens. Parse takes a list of tokens and returns either error or AST. And the type check takes the AST and returns either an error or a typed AST. We want to compose these functions so that they can work in a chain. The output of tokenize goes to parse, and the output of parse goes to type check. We know that we can leave a function over an either and other functors. We can also leave the function that returns an either. If we take an fmap and apply it to parse and tokenize string, we get an either error of either error or AST. If we compare with specialized version of either error, A is a list of tokens and B is either error or AST. While this code compiles, it's not great, because we are building layers of either errors. We also cannot use this trick again with a type check, because type check is gonna expect an AST, but if we try to fmap it on what we have here, the A will be already either of error AST, which doesn't match with AST. What we would really like to is to flatten this structure instead of nesting it. If we look at the kind of values either error or AST could have, it looks something like this. It's either left of an error, right of a left of an error, or right of AST. Okay, what if we just use pattern match for this instead? What would this look like? So first we tokenize the string and then we pattern match on the result. If it was a left, we return the left, and if it was right, then we get tokens, and we can parse these tokens and pattern match on it again. If it was a left, we return the left again, and if it's right, it means we have an AST, and we can type check this AST. In this case, we don't have to pattern match because the last result is already an either of what we want, so we're gonna get what we need. So if we run into an error in a stage, we return that error and stop, and if we succeed, we use this value in the next stage. Flattening the structure of either is very similar to this last part, the body of the right tokens case. If we had an error, we propagate this error, and if we had a value, tear this one layer out. And because we have this function, we can now use it on the output of fmap parse tokenized string from before. Flattening will give us the either error AST. And now we can use this function again to compose with type check. This flatten plus fmap combination looks like a recurring pattern which we can combine into a function. This flat map takes a function and a value. First it fmaps the function and then it flattens what it got. And now we can write the code this way. First we tokenize, then we flat map parse, and then we flat map type check. Using backtick syntax, we can convert the function to the infix form to make the chaining more clear. Tokenize string, flat map parse, flat map type check, or create a custom infix operator. These functions, flatten and flatmap, have different names in Haskell. They are called join and reverse bind, and they are the essence of another incredible useful abstraction in Haskell. If we have a type that can implement the functor instance, specifically the fmap function, the applicative interface, most importantly the pure function, and the join function, they can implement an instance of the monad type class. With functors, we were able to lift a functions to work over the type implementing the functor type class. With applicative functor, we were able to lift a function of multiple arguments over multiple values of a type, implementing the applicative functor type class, and also lift a value into that type. With monads, we can now flatten or join, in Haskell terminology, types that implement the monad interface. And note the operator called bind, which has reverse arguments from the operator we created and saw before. With bind, we can write our compilation pipeline from before in the left to right manner, which seems to be more popular with monads. Tokenize string, parse, and type check. We already met this function before when we talked about I/O. Yes, I/O also implements the monad interface. The interface for I/O helped us with creating a proper ordering of effects. The essence of the monad interface is this join and bind functions, and as we've seen, we can implement bind in terms of join, but we can also implement join in terms of bind. Feel free to try it as an exercise. The monadic interface can mean very different things for different types. For I/O, this is ordering of effects. For either, it's an early cutoff. For something like logic, this means backtracking computation, etc. Again, don't worry about analogies and metaphors. Focus on the API and the laws. And if you explore it on your own, maybe you already seen monad laws, but I'll just mention it. Monad has left identity, right identity, and associativity laws, similar to the monoid type class we saw before. Feel free to explore it on your own. And remember the do notation? It turns out that it works for any type that is an instance of a monad. How cool is that? Instead of writing the pipeline using binds, we can write the pipeline using do notation, and it still works. Still, in this particular case, this version is so concise that it can only be beaten by using classly arrows, which might remind you to function composition and allows you to make this code even shorter if you want to or need to. You don't really need to. You can write Haskell perfectly fine without knowing these operators. But Haskell ability to create very concise code using abstraction is great once one is familiar with abstractions. Knowing the monad abstraction, we are now already familiar with the core composition API for many libraries. For example, concurrent and asynchronous programming, web programming, testing, emulating stateful computations, sharing environment between computations, and many more. And in summary, using either for error handling is useful for two reasons. We encode possible errors using types, and we force users to acknowledge and handle them, thus making our code more resilient to crashes and bad behaviors. The functor, applicative, and monad interfaces provide us with mechanisms for composing functions that might fail, almost effortlessly, reducing boilerplate while maintaining strong guarantees about our code and delaying the need to handle errors until it's appropriate. In the next part, we'll talk about more ways of handling errors, using either with I/O, without I/O, and exceptions.